Hello everybody, how y'all doing? Hope you are all having a great time. Today we're gonna start preparing for midterm 2 for calculus. Uh this shouldn't be that bad. I feel like this midterm 2 should be a little bit easier than midterm 1. Reason being is because most of these things are memorize, practice, and you're done. Not necessarily memorize. It's better if you understand it, but if you memorize it, you could definitely get 100 on this midterm just by memorizing. Because these are usually do these steps and you'll get the answer regardless. There isn't a lot of application. Actually, I would say there is some application, but they're very similar to each other, so you should be fine anyways. I haven't covered all the midterm 2 material yet, so maybe I'll come up with things that don't apply to what I just said. So we'll get there in a couple days. Today we are doing introduction to differential equations. So, what is a differential equation? What makes a differential equation is having one or more derivative. So, remember before you would have f of x equals, let's say, x squared. This is one derivative. This is actually a differential equation. What does it mean, differential equation? If you go on Google and literally search the meaning of differential, is the difference between 2 points. Okay, and so the derivative is actually the slope or the difference between 2 points. And so you see, when you integrate this, you'll do the integral and you'll do a and b, and this will give you the difference of the 2 points. And so you could have an equation with multiple derivatives, like y prime plus y equals y double prime. I don't know if this is an actual equation, but this is a differential equation if you want to identify it. And what makes the differential equation different from other equations is that when I give you y equals x squared, let's say, when I want a solution for this, I'm looking for a number solution, like a numerical value. But when it comes to differential equations, the solution is actually an equation. An equation is the solution. All right, and we'll get to it. It's actually the easiest part about differential equations. So here, the order of a differential equation is just the maximum derivatives there is. And so when you look at this is no derivative, right? This is a third derivative, so the order is a 3. This is second derivative. This is 6. That is 6, and this is 2. This is 1. This is an exponent. Because if it was, it would look like this if it was a order, but it's not. It's an exponent, and so this would be just 2. All right, so far so good. If you mess this up, you're actually an idiot. But okay, yeah, go back to high school. Anyways, so the rate of change of a population p. So there's a couple things with these type of questions is they follow the same syntax. I call it. I'm a programmer, so syntax is the way to go. So yeah, same syntax. So when it says rate of change of population p, as soon as you see a rate of change here, this is dp over, so this is of population over your independent. So in terms of y and x, dy is the dependent, dx is the independent. You could also have, like in our case, let's say like dp over dt. The time is independent, it doesn't change. So that's how you decide what goes at the bottom and what goes at the top. Whatever doesn't change with regarding to the other one is the independent, and it goes to the bottom. So the rate of change of a population, with respect, well, it tells you with respect to time. But even if it didn't tell you this, the rate of change of the population changes with, over time. So over, literally, population over time. And so the language itself, like you could definitely, like it tells you the answer. And when it says proportional, this means is the same thing as saying equals to. Proportional, and if you even search up what proportional means in English, you'll find out it means it's something equal to something. And so it's equal to the population itself. So p. But this doesn't make sense, because when you are looking at dp over dt equals p, let's say you have 1,000,000 people, or actually let's say you have 1,000 people. When the population increases, it's 1,000 people, and let's say it increases by a constant like k. And so when you do k times 1,000 people, let's say the constant was 2, out of every 1,000 you will get 2,000 people over some period of time. And so this constant is usually your k, and an integral, that's your plus c. The reason being is because when you, up here, when I was saying about integrating, you get, when you integrate, let's say x squared, you'll get 1 over, oh, it's wrong syntax, but you'll get y equals 1 over 3x3. But then you have your plus c, because integration gives you a family of functions. And your plus c tells you exactly, if you have a c, it tells you exactly which family it is, or which function it is. And so, same thing here, the solution is an equation, but it's a family of equations, and that's what your k is. It's just we don't do plus k, we do times k in differential equations. All right? And so it's the same thing here. It's like, you know how don't forget your c, don't forget your k. And so a cup of coffee at temperature T, so it tells us a cup of coffee, we have temperature T, that's the coffee cup temperature, and it cools proportionately, which means it equals to the temperature difference between it and its surroundings. So first, let's map out this part right here. Well, this part. Temperature difference between it and its difference. So I'm gonna teach you guys some high school stuff. If you have a point A, and this is point A, let's call this like a distance x, and you have a point B here. All right, and this is like the initial, this is 0, and this is, let's say, like 11 meters, and this is like 20 meters or some shit. All right, so when I tell you the difference between these 2 points, you take B minus A, that would be your difference. Okay, so same thing with temperature. You will take your T minus, it literally says the difference, temperature difference between it, which is T, and its surroundings, minus its surroundings. So that's our first part. Now it's proportional to, so that's equals, like I said, your constant, don't forget your k, right? And then what we'll do here is, your dt, oops, so this would be actually capital T, because we're looking for the cup of coffee temperature, and it's over dt. I forgot the word for it. I just used the word earlier. You know what? It is what it is. And you're like, oh, how did you find this? Is because we're looking for how fast the temperature, like it says, temperature T cools, and it cools over time. Like there's this is your independent. Like you see, this is a great example of, it doesn't have to be always over T. This is an example where it's not over T. And here it says the force exerted by the spring. So the force exerted by the spring, this is equilibrium, and then you pull it that way, as you can see in the arrow, by a spring, is proportional to its displacement from the rest position. Its displacement from the rest position. And so don't forget your k. All right. Now, if you want to be accurate with directions, you see how the displacement goes that way, but the force goes left? So if you keep your displacement positive, so if you say x is positive in this direction, then your force, we're representing force has to be negative because it's backwards. You know, when you pull a spring, when you push a spring that way, the force is going to exert when you let it go is the opposite direction. Now, the other way you could say is distance is negative in this direction. And you would basically, and you would basically remove this, and you would get instead k minus x, which is the same thing, but this is the mental behind it. And here, if you want to go, hence its acceleration, if you want to go to and like take a step further, you could do, Newton's second law. If you've taken physics, ma equals k, so negative k minus x. And if you want to go even a step further, because here you have two unknowns, you have a and x, and if you want to put everything in terms of x, mass, I'm pretty sure mass is constant, because mass doesn't change, and this is also constant, so you put everything in terms of x. And we can say, displacement, if you derive displacement, you'll get velocity. If you derive it again, or if you derive velocity once, you'll get acceleration. So in differential equation terms, m x, second order, equals minus kx. This is the same thing as saying this, because your a is the second derivative of your displacement. All right. This one, I don't know what was up with the prof. I think she lost her mind on this question. It's not too bad, but it's a little, you need some background knowledge, I would say. So, but here, we'll go into it. The rate of spread of the flu in a community of total size n is proportional to the number of infected and the susceptible individuals. So, n is proportional to number of infected and the susceptible individuals. This is our equation number one. Now, our equation number two would be your DI, because we're looking, so if you're looking for S, it would be DS. If you're looking for I, it would be DI. If you're looking for the infected, you would do DI. If you're looking for the susceptible, you would do DS over time. But your DS doesn't depend on the flu, which is kind of counterproductive, so you wouldn't do that. But it would be DI over DT equals to your constant. Your constant is always there. And here is where you need background knowledge. What I'm going to do is I times S. And this is the SIR method, or equation. And this is to represent epidemic equations. And they're multiplied. They're not always multiplied. And so you need like some background knowledge to know this. I don't know why she did that. Because like nowhere, like if you take this text and you search it online and you put it through whatever website you got, they will tell you like this is vague, but if you had to guess, it would be multiply. Like, because here it says and this represents this equation. But if you have some background knowledge, you would know it's time. So if you didn't figure this out, that's fine. But obviously here we have two unknowns and we're in terms of I. So, and since we have a second equation, we can rearrange this. Take our I to the second side. This would be n minus I equals S. And so di over dt equals our constant I times, we're going to replace our S with this equation, which is n minus I. And your n is constant because it's the total size of n. Unless people are constantly giving babies, this stays constant. Right? Or what you could do is you have another equation, like you know how we have a population equation right here. You could take this equation and you would sub it into your total population or community size. And so this is how you have like two equations within one, but differential equation. Okay. This is also the second easiest part. So the first easiest part was this. This is the second easiest part. The only thing you need to know about this is one, you know how to simplify equations, and two, you know how to derive. That's the only two things you need to know. You know how to do these, you should get 100 on this. So determine whether y is a solution of y prime 3xy. So you know how you said sometimes, like if I give you y equals x, and I want to find a solution, I'll give you some point, and I'll tell you find this. Here, they're doing the same thing. They're giving you the equation, and that's equivalent to this, and they're giving you a value, which is equivalent to these coordinates, and saying, see if this goes into this. And the way you would do it is you just sub it in. So this says y prime, so you derive this. So here, we'll do y prime equals to, so here we have 5ex squared. So this is actually not y prime yet. Right? This is not y prime yet. And then when we derive it, what happens is your x comes down and you multiply by the derivative of x. So this would be e to the x squared multiplied by x squared, the derivative of it. That is your, I believe this is chain rule or exponential rule. I'm not sure what the name is, but I know this is the way. So if you want the exact name, you can go search it up. But anyway, so when you derive this, the 2 comes down and you minus the 2. So this becomes actually, the derivative of this is 2x, right? This 2, so this will become 5e x squared times 2x. The 2 can expand in, so it's become 10e x to the 2 times x. That is your y prime, right? Now that we found our first order, and we already have our y, which is right here, all you got to do is sub them in. So we have y prime, which is 10e x squared times x equals 3x. And now we sub in our y, which is 5e x to the 2. Now this 5 and this 3 can multiply. This is called, you see, this is the simplification part. This is an easy example, but you'll see harder ones. Equals to 15. And this would be e x squared times x, and this x would come from here. And you see this clearly does not equal this. These parts equal each other, but this 10 and 15 is not the same. So what you say is 5e x to the 2 is not a solution to, your y prime equals 3xy. And that's the most you would do. Actually, no, this is not the most you would do, because sometimes simplification can get a little bit harder. This is the second way you might encounter. So here, what value of r is y equals e to the rt is the solution of this. But here they're specifically asking what value of r. So r is actually a constant, and t is your variable. All right, because we're looking for values of r, and so it has to be a constant into 2 equations or 3 equations or however many equations we find. But your t is like your x, it's your independent. And so what happens is we're looking for a second derivative, a first derivative, and a zero derivative, or your original function, in other words. So original function, e r t, that looks like an n, but it's an r. All right, and so our first derivative, this comes down and you multiply by the derivative. RT's derivative is actually just r, because this is constant stays. Your t derivative would be 1 minus 1, which is 0. And so t becomes 1. That's what it looks like. It's r1, but you don't write the 1. So this will look like r e r to the t. That's our first one. And our second one is basically this times another one. Well, not times, but something like this. Actually, it would work as time as well. Does it? No, it doesn't. Yeah, maybe I went overboard here. But basically, your second derivative is you would take this and you would derive it again. And this, for e-ruler, you take this down, do the same thing, you only get r1, multiply them. I hope you guys are familiar with this. I'm not trying to go too much in detail because I'm assuming you already know your derivatives. This would be r squared e r to the t. Now we got all 3 of them. We sub them in. R squared e r to the t plus 2, the first one, r e r to the t, minus 3 e to the rt equals 0. So now if, let's say I didn't have a 2 here and I had like an r here, I can technically minus this one from this one. I'll get a -1, then I'll have a +1 here, and this would technically equal 0. But that's not the case. This is what I look like, and I'm not even looking if this is a solution. I'm looking for what values of r is this a solution. So what we can do is here you can see like we have these are commons in all 3. So let's pull these motherfuckers out. So this is pulled out. Now you get r squared plus plus 2r minus 3, and now you have a quadratic equation. How nice. Or is it algebraic equation? You know what? I'm not good with terminologies, but you get the point. You can simplify this. You learned this in grade 9. And so e to the rt stays. I'm just simplifying that. And so here, you get r, what is this? -1 +1. I believe this is +3 and r -1. That took me a little bit, a while to process, not gonna lie. Okay, so now this, you can, because they're multiplying, if these were adding, you can't do what I'm about to do, but since these are multiplying, this goes to infinity. This r equals -3, and this is r equals 1. And now we found, well, this is infinity, so we don't count this. We found 2 values. You take these and you sub them in your original. So you say e to the -3t, that's this, subbing in -3, and e to the 1, you sub in 1 for r, and t, you don't have to write the 1, but in case, I just wrote it so you guys can see it. Now we found the values, the 2 values. These 2 equations are solutions. Solutions to, you know, our second order plus 2y first order minus 3y equals 0. All right, and that's that for this. So basically, what you could do to confirm this, I will do it down here. Actually, yeah, I'll do it down here. So if I take this and I sub it into here, so you know, y equals e negative 3t, right? Our first one would equal negative 3e. I'm just doing this quick just to confirm and show you guys how to confirm your answer. That's what it looks like. And our second one would be this 3 times 3. That would give us 9. Negative and negative, that would be positive. So 9e negative 3t. Now we sub them in. And you see what we're going to do is 9e negative 3t plus 2 y, the first one. So it would be negative 3e negative 3t. And we have minus 3 of our original, which is, and that's what it looks like. All right, now to simplify, we have the 9. This multiplies in. So this stays the same. This multiplies in, it becomes a negative 6e to the negative 3t. And this stays the same, which is negative 3e negative 3t equals 0. All right, now this term minus this term will give us, so this what this will look like. Don't forget this part. So 9e to the negative 3t. I just brought this from here. Same. And then I'm going to do this minus this. Stays a minus. 9e to the negative 3t equals 0. Now, positive minus the same thing. 0 equals 0. That satisfies. And so it makes sense. And so that's how you can check your answer. And if you guys want on your own time, you can check the second answer up here, sub it in, and see if you get the same thing, which you should. All right. Now, this is problem number 2. Let me see how much time I'm in right now, just to make sure the video is not too long. 22 minutes. I mean, this is supposed to be a lecture, so hour 40. This example I find a little bit stupid because it says, oh, how do we actually do this? And some basics like this. This is supposed to be an easy differential equation. We can reason out the solution. I mean, if I'm trying to reason out the solution, I'll say, well, this is what? K, E. What can you do here? Like 2t? Or you can do 2x or 2 whatever variable you choose. Because when you derive this, this will look like K 2, because the 2 will come down when you get the derivative of that, because we're looking for, you know, our y prime, because the equation asks for the first y order. So this would be k 2e to the 2t. And so when we sub it in, we already have our y, you know, y prime equals 2y, and this would equal k 2e 2t equals, we bring in the 2, and we get the same equation from here. 2t, and you see these are equal to each other. Like if you flip this here and you flip this here, you get, you know, this is the same. And you see, we just reasoned out an equation, but I think that she's stupid for doing that, because I mean, you guys are just doing differential equation for the first time, and unless you're a genius like me, you're gonna look at this, you're like, how the fuck do I know what to do? And so this is kind of stupid. Don't worry about this, because it literally says we will learn method to next class that will focus on numerical and graphical approaches, that so other methods to, you can reason out what the solution is, and you can use the same method to apply it to this to find this solution without you having mentally do it. And that's the whole point, is that even as a mathematician, if you mentally do it, you still have to prove it. So retarded question. Anyways, next question. We already know how to solve the solution, blah blah blah, general solutions. We already spoke about this, you know. We said like y prime equals x squared. This is a differential equation. Oh my god, my monitor was about to fall off. Don't ask me how. Unless you see my setup, you'll understand. But you see, like, this is a differential equation. This is the same as this, by the way. These are equal. Yeah, and so this, because it has one derivative, this is a differential equation. It doesn't have to have, like you see how y prime equals x squared. I don't have to have a y here or a y here to make it a differential equation. As soon as it has one derivative, differential equation. All right. And so this is like, you know, like simple general solution, like what do you call it? Differential equations. Now here, initial value problems. This is what happens with your so that you know what this looks like? This looks like a integral. So you know when you do an integral, like you do your a b of some equation, and let's say I integrate this, and this equals 1 over 3 x to the 3 plus c. This plus c, because what this gives you a family of functions. A family of functions, multiple functions. And this plus c determines what function you're using. So you see, if I go to at x0 and y1, and if I go x0 and y1, there's only this one function that exists here. And so if I give you a point, any point I give you, so I know that the teacher used a point of 0 and 9. So if we use this point and we sub it in here, so this is, since we integrated it, this is y, no longer y prime, because it's an integral, like it's an integrated method. So it's 1 over 3 x cubed plus c. This is what it looks like. I have my y and x, so my y would be 9, my x would be 0. Since my x is 0 cubed, still 0, times 1 over 3, still 0. So you get 9 equals c. Now, your equation, this is your equation now. It doesn't have that unknown constant c or variable c. This is what it looks like. And this will give you only one function. So if you plot this, it will give you like one function. But if you plot this, it will give you a family of functions. And so that is IVP. And this is just a recall. So this is not a part of the midterm, I don't think. Here it's saying, oh, how do we find more complex stuff? And she showed us a pretty weird, dumb example, I would say, because we are going to learn the proper way to do it. This is now we're doing direction and field. Direction and field here, you basically just follow the goddamn arrows. So you see this arrow goes like this, and these arrows explain the slope. So each arrow, like you see here, the slope is negative. Here the slope is positive. What other example right here we have? Let's see. I mean, yeah, most of these examples is negative. Pointing upwards is positive. Sometimes you'll have it like pointing like straight like this or slightly down. This you can consider like a zero slope, so like there's no slope. I believe if it's a vertical up like this makes it a asymptote. There's two asymptotes here. Vertical, and that's that. Pretty simple. I'm not gonna go too much into it because I mean, you just follow the arrows. Like there's nothing much to learn from this here. It literally says, you know, it's a direction field or slope field. So each arrow is a slope. And basically, if you take a function like y equals x squared and you derive it, it will give you, so this will give you some graph, which I believe is like a parabola. And if you take it and you derive it, it will give you a drawing of the slopes. So you see the slope here is how it's like this. And then the slope here is like, it's negative. And here's negative. Here it's like the slope is 0. And here's the slope is like positive, and the slope is positive, and it gets steeper. So it gives you the graph, and this I believe would look like linear, like it's a linear when you, yeah, because when you take this and you derive it, you'll get y prime equals 2x, which is a linear function, and it increases constantly because you see here the slope is negative, and it keeps increasing 0, and it increases even though you see here it decreases and increases. But it goes from a negative slope to a positive slope, and from a negative slope to a positive slope, from a negative number to a positive number. And okay, so I'm gonna go to the next one. Don't worry too much about this. It's just a drawing. We'll go more complex, like here down here. You see, we actually get equations, and this is where you'll actually understand the concept of this. And yeah. So what do we have here? If we draw a function that satisfies, suppose we wanted to know if a given direction field matched a given differential equation, what would we look for to make our decision? So she did write a list of all the things you would look for on her thing, so I'm not going to go through them. I'm going to go through how to use them. And that's what we're going to do here. So we're going to start, what you want to do is start with the most obvious one. And so you see here, these don't look as obvious. Like this one is a little bit more obvious. We'll talk about why. But you see, this one I would say is the most obvious one. I'm actually bored of the color blue, so I'm gonna change it to green. That's duh, it can't be green. Anyways, so you see here, this has a denominator. And we know, typical math, if you divide anything by 0, it's the calculator is gonna tell you what the fuck. And so let's make this 0. How do we make this 0? 2 plus y. What does y have to be 0? Y has to be negative 2. This would equal to 0, right? I'm going to remove this because you probably already know this. I just wanted to do it to make a point. And so what we know now, that if y is negative 2, our solution is unknown. And so here, at negative 2, our slope is known. That's fine. At negative 2, slope is known. That's fine. At negative 2, slope is still known. That's still fine. But here at negative 2, look how like the slope goes negative, positive, and like what is this? I've never seen a function with 4 goddamn slopes in the same spot. So this clearly should throw you off and be like, huh, what is it? Like, look, here they're coming towards each other, here they're going apart from each other. And so at negative 2, it's clearly unknown, undefined. And so that's how you would know here. And so this is what confirms and tells you this must be A, because nothing else is undefined at 2. Now, what about the rest of them? You see, we can start at this. This is the odd one because it doesn't have x. And, okay, so if it doesn't have x, that means it's not dependent on x. That means it doesn't matter where you are on the x, the slope doesn't differentiate. And you see here, as we move on the x, so not the y, so we're talking about just this row. Or actually, I'm going to talk to a more obvious row. So, like something in the middle here. This is a little bit more obvious. So let's take this row. And as I move along the x, the slope changes. And so this does depend on the x. And so if I go here, same thing. I take one row and I highlight it. And I go, if I move along the x, this changes along the x. But you see, if I go here and I highlight this, you see along the x it's all the same because the equation does not depend on x. And so that's how you know that this equation is indeed C. Another way to check is you can see this is 1 plus a squared y. A squared y means no matter what y is, so y can be negative 100, but because we have a squared, this will always be positive. And then we're also adding it to 1. So this tells you two things. Your slope, so y prime is the slope, your slope can never be 0 because of the plus 1. Like if this was 0, 0 plus 1 is 1. So the minimum slope you get is 1, and your slope can never be negative. A negative slope points downwards. You see this, it doesn't point downwards anywhere, nor is the slope 0. So a horizontal arrow means it's 0, and you don't see it's not 0 anywhere. And so that's that. So that's C, we found that. Now we have B, and we have D. And these I wouldn't say as obvious. How can you tell the difference? For me, what I like to do is I'll just choose a random point and see if it equals my slope. So what can we do here? 0, 0 is usually the easiest one. So you see here, if I plug in, well, this one in specific. So you see in your cos here, if x was 0 and your y was 0, this whole thing would equal 0, right? And cos of 0 is 1. So at the point 0, either here or here, my slope is supposed to be 1. And you see here, this slope is a positive. So you see like this. What makes a slope 1 is rise over run. So run over rise, 1 by 1 makes this 1 because, you know, if you do your hypotenuse theorem or whatever, you would actually get a 1 when you do the Pythagorean theorem. And so, anyways, so this gives us a slope of 1. But you see this, the slope here is actually 0. And the other way you can check is this one. If y is 0 at some point of x, so at anywhere on x, so let's take x here. So this is my x. Anywhere on x where it's close to 0, this will always give me 0. Because if y is 0 times x, this whole thing becomes 0. And so all along the x, whenever y is 0, x, the slope should always be 0. And you see here, it's all 0 along the x close to my my y0. And it's vice versa as well. like if you see here along my y, so let me choose a different color so it's easier to see. Along my y here, along my y, whenever x is 0, so you see at this point x is 0, the slope is 0, because if x is 0 times y of whatever number will equal 0. So even at y3, my slope is 0. And so that gives it away. That tells you this is supposed to be D and this is B. And that's how you do this one. Euler's method. Euler's method is actually 3 marks. Like this first lecture of differentials is all 3 marks. If you ever see this, 3 marks. I'm not gonna go through this because she tells you the hypothetical idea of what goes on, but I strongly believe if I show you this example, you'll understand what's going on. And so we'll go through this example. This equation basically says, well, the thing is, like, okay, so for most students, when they read n minus 1, they're like, oh, this looks scary. N in this, in Euler's method, n identifies the steps. So you see here, it's step n. So it's literally like, it's steps, and n is the steps. So yn is the current step. So it would be y current, n current step, equals n minus 1 means y from last step. Because if this is the current step and you minus 1, that is the last step, right? And so it's y last step. And you'll see more into it. H is a constant. So h is h, whatever they give you to be h is h. Sometimes you'll have to find h, so you find h. This equation, what it says, this equals, so if I give you like y prime equals x, I don't know what's up with this example, but I'm gonna keep using it. But let's say I give you this example. What this says is use x from last step, and use y from last step. I know this is hard to read. I'm writing using my mouse, by the way, so you should be proud. And so what it tells you is use x from last step and y from last step and sub it into the equation and give me the answer. That's what this equals to. So if I had another y here, let's say this is my differential equation, I would use x from last step, sub it into my x, use y from my last step, sub it into here, and that will give me my f. It's just like saying f derivative of x, right? It's the same thing. And that's what it gives you. And so that's what you have here is, you know, it's your whatever the equation is, and you pass it these two parameters. And so when we go down here, we have this equation. I'll use the same. We have this equation, and it tells you start at this. So it tells you an x as the first step. So that's your first one, right? And it tells you at your first step, your y is 1. Okay? And this is step 0. We're just starting, nothing special. We're just identifying things. And it's saying approximate. So what Euler's number does is it gives you an approximation. All right? And we'll get more into how accurate this approximation is. But so it tells you give me an expression at x equals 0.25 with a step difference of 0.25. That's your h constant. And so your xn, even up here, it says your xn is your last step plus your h. So my step 1, right, this is my current step now. And then what's my xn here? It's my current, it's my last plus my constant h. You see, it's my last plus h. My last is 0 plus my h. And this will give us 0.25. Right? Now my y, what it says, is equal to, so it would be y of the current step. We don't have that. That's what we're looking for, right? This is what we're looking for. Y of the current step. It equals to y from last step, which is 1, plus my constant, h. And then this is the equation. So it tells you the equation is y plus x2. What do you sub here is we said x from last and y from last. You see? You sub x from last and y from last. So x from last is 0. Y from last is 1. So what this gives you, this equals to 1 plus our h, 0.25, times 0 plus 1 is 1. Right? This is what it gives you, which equals to 1 times 0.5. This is like doing 25% of 1, which is 0.25. And Or the other way you can think about it is anything times 1 is the same. Lol. My mentality is a little bit weird sometimes. Plus 1, so 0.5 plus 1 is 2.5. So that's our first example. Second, so this is now our second step, is our x is x from last step, which is 0.25, plus our h, which equals 0.5, right? Now our yn equals to my y from last step, this is my y from last step, plus h is a constant, right? Times the function at the given values, at the last values. So this would be y from the last, which is 1.25, plus x from the last, which is 0.25 squared, right? And so you do this math, and this should equal, I have it written on the side, so I don't waste time doing the math, but that's, oops, that's the wrong one. Oops. 0.578125, right? And if you do 3 here, same thing, x from the last 0.5 plus this 0.75. Watch this. This is equal to what we're looking for. And so they're saying find an approximation value. So we're looking for our y at this location. And so our yn, which is what we're looking for, is our y from last plus our constant. And then here we have our 1 point, well, we don't use this. We use this equation, but it takes y from last. So 1.578125, see? Takes y from last plus our x from last, which is 0.5 squared. And this will equal to 2.035 15625, and that is your solution. That is your approximation at your 0.5. There you go. Okay. This exercise is the same steps over and over again, except it tells you start from this. So if you guys wanna, this is on your lecture notes. That's why I'm not gonna keep it. Because I am going to use this board to do this step under. I'm not going to finish the step under. I'm just going to show you what's different about it. All right. And there you go. And so you see here, what it says is you start, so it's your step 0. You start at x being 1 and your y being 3. And tells you approximate up to x equals 1.4, right? And it tells you step by 0.1. So 1, this would be 1.1, and then you add the last one plus h. This is 1.1 plus our 0.1, which is 1.2. That's our xn. And this is 1.2 plus 0.1, so this is 1.3. And then you'll have another, can't draw, but you get the point. This would be 1.4. This is what we're looking for. You see here? That is what we're looking for. So you want to find, that's a horrible circle. You want to find the x value at this step. And the x value would be the same. Everything is the same, except now you have a different equation that you sub in. And you sub in the last values. Don't forget. Like here, I'll do this one step. You would use your y from the last, which is this, plus our h down here, which is 0.1. And the equation is x. What do you plug in for x? Is the x from last, which is 1. X from last. And then y, what do you plug in for y? Is y from last. This is times 3 minus 2. And you calculate this whole thing, and that's your first answer. And you keep going in loops, so step 1, 2, 3, and until you get to step 4, and that would be your solution. The other thing, what h, in case this is a multiple choice question, h, the higher h is, the more accurate, the less accurate you get. So if my h here was 1, the solution I would get is so inaccurate. So let's say I have this equation, and my step was 1. So I'll get, the slope here is like this, then I calculate it again. So you see how I am moving by 1? So I would move literally by 1. So 1, what is the slope between here? Let's say the slope between here is like something like this. So that's this, I calculate the slope here, right? And then what I'm going to calculate is plus 1 again. So from 1 to 2. The slope here is, let's say like that. That is the second slope. And then I look for now slope from 2 to 3. and this gets you less accurate. The more small, so like if this was 0.01, it would give us something like so close, because you're calculating the slope. You see the difference here? I'm calculating the slope every 1. But if I calculate the slope every 0.1, I'll have like small slopes that like are, it gets more accurate as the number gets smaller. And now this is very helpful with computers because it will show us very accurate results depending on the equation. And that is lesson number, or lecture number 1 for midterm 2 calculus.